Just a photon has a momentum as well as wavelength. Electron should also have momentum as well as wavelength. The energy of orbitals in multi-electron atoms with the quantum numbers. The orbital with a lower n plus L value has a lower energy and gets filled fast if there are 2 electrons in one orbital. They must spin opposite direction. Hello students, I am Ramya, lecturer in chemistry from Vidhyaashram, the Temple of Excellence, Mysuru. In the previous session, we have discussed about Planck's constant, photoelectric current, dual behavior of electromagnetic spectrum, atomic spectrum, Bohr's model of an atom, postulates of Bohr's model, limitations of Bohr's model. In this session, we are going to discuss about de Broglie concepts of dual nature of matter, Heisenberg uncertainty principle, quantum mechanical model of an atom, quantum numbers, electronic configuration of atom, Hund's rule of maximum multiplicity, Pauli's exclusion principle. Towards the quantum mechanical model of an atom, this model was based on two concepts: de Broglie concepts of dual nature of matter, Heisenberg uncertainty principle. Dual behavior of matter. The French physicist de Broglie in 1924 proposed that matter should also exhibit dual behavior, that is, both particle and wave nature are wave-like properties. De Broglie equation. It means that just a photon has a momentum as well as wavelength. Electron should also have momentum as well as wavelength. De Broglie, based on this analogy, gave a following relation between the wavelength and momentum of the material particle. Y equals h by mv, that is equals to h by p. Here, where m is the mass of the particle, where v is its velocity and p is the momentum. Important note, de Broglie predictions was confirmed experimentally when it was found that electron beam undergoes diffraction, a phenomenon characteristics of wave. Every object in a motion has wave character. The wavelength associated with our ordinary objects so short because of their large mass that their wave properties cannot be detected. Heisenberg's uncertainty principle. Werner Heisenberg, German physicist, in 1927 states uncertainty principle, which has consequence of dual behavior of matter and radiation. It states that it is impossible to determine simultaneously the exact position and momentum of an electron or the velocity of an electron. Mathematically, it is given as in equation delta x into delta p x, that is greater than or equal to h, or delta x into delta m x, that is greater than or equal to h, or delta x into delta vx, that is greater than or equal to h, where x is the uncertainty position and delta px or delta vx is the uncertainty momentum of the particle. Explanation. Suppose we attempt to measure both position and momentum of an electron. To pinpoint the position of the electron, we have used light so that the photon of a light strikes the electron and reflected to the photon is seen in the microscope. As a result of hitting the position as well as the velocity of the electron are disturbed. Significance of uncertainty principle. It's ruled out that existence definite paths and transactions of electron and the other similar particles. The effect of Heisenberg uncertainty principle is significant only for a microscopic objects and negligible for macroscopic objects. Reasons for the failure of Bohr's model. The wave character of electron not considered in the Bohr model. According to Bohr model, an object is clearly defined. The path and its path can completely determine only both the position and velocity of the electron are known exactly at the time. This is not impossible according to the Heisenberg uncertainty principle. Quantum mechanical model of an atom. Quantum mechanics is a theoretical science that deals with the study of motions of the microscopic objects that have both observable wave-like and particle-like properties. Quantum numbers. To obtain complete information about electron in an atom, 4 identification numbers required. These identification numbers are called quantum numbers. These are principal quantum number denoted by N, that is shell, azimuthal quantum number denoted by F, that is subshell, magnetic quantum number denoted by M, that is orbital, spin quantum number, that is S, spin of the electron, that is S orbital, P orbital and D orbital. Principal quantum number. This quantum number tells energy level or a shell which electron belong, n equals to 1, 2, 3 etc. that is K, L, M, N etc. This is also give the information about average distance of an electron from the nucleus in particular shell. Maximum number of electrons present in the given shell is given by 2n square. The number of orbital in a shell is given by n square. So, if we consider n, the shell number and the total number of orbital in the shell, that is n square, maximum number of electron, that is 2n square. So, the value of n, that is 1, 2, 3, 4, it is considered as k element shell. The total number of orbit in k element shell 1, 4, 9, 16 respectively by taking the value of n equals 1, 2, 3, 4. The maximum number of electron, that is 2n square equals 2, 8, 18 and 3. Azimuthal quantum number or subshell or orbital angular quantum number. It gives the information about number of subshell, angular momentum of the electron, the shape of the various orbital, the energy of orbitals in multi-electron atoms with the quantum numbers, the number of orbital in a subshell, that is 2l plus 1. For a given value of nl have n values ranging from 0 to n minus 1. The total number of subshell in a particular shell is equal to value of n. Subshell notation. So, if the value of n equals to 1 and l equals to 0, that is subshell notation 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d and 4f. The shell number, that is value of L equals SPDFG, that is 0, 1, 2, 3, 4 respectively. The number of orbitals, that is 1, 3, 5, 7, 9 respectively. Magnetic quantum number. It gives the information about the number of preferred orientation of the electron in subshell. Each orientation corresponds to the orbital. Therefore, ml gives the number of orbital in a subshell for any subshell, that is 2l plus l value m are possible. Magnetic quantum number. The magnetic quantum number, that is m1 sub level s, that is l equals 0, m equals 0, subshell p, that is 1, m equals 0 minus 1 plus 1, D 2 minus 2 minus 1, 0 plus 1 plus 2, F 3 minus 3 minus 2 minus 1, 0 plus 1 plus 2 plus 3, like that. Electron spin quantum number. It refers to the orientation of spin of an electron. It can have two values, that is plus half or minus half. Identify the anti-clockwise direction. So, if the plus sign is there with the half, it considered as clockwise direction movement of an electron. If the minus half is there, it is considered as anti-clockwise direction of movement of electron. Electronic configuration. The arrangement of electron in a atom orbital. The most stable state in a ground state, which is determined the several quantum number, that is Hofbauer principle. The Hofbauer principle states that the ground state of an atom electron filled atomic orbital from the lowest available energy level before occupying the highest energy level. Electrons fill in the lowest energy orbital first and only move the higher energy level or orbital, then lower orbital fully occupied. The general order of orbital filling is 1s, 2s, 2p, 3x, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p and 7s, etc. This sequence comes directly from the n plus L rule. N plus L rule, the orbital with a lower n plus L value has the lower energy and gets filled first. If the two orbitals have same n plus L value, the orbital with a smaller principal quantum number, that is n value, shows the electron filled first. That means it is nearer to the nucleus. Example, 4s versus 3d. 4s orbital having n equals 4 and L equals 0. That is s orbital. N plus L value for 4s orbital, that is 4 plus 0, that is equal to 4. For 3d orbital, n equals 3, L equals 2. The d orbital, n plus L value, that is 3 plus 2 value having 5. Since 4s and 3d orbital shows the 4s orbital is a lower energy and filled first. That means electron filled for 4s orbital first, then it goes to the 3d orbital. Pauli's exclusion principle. No two electron in an atom have same set of 4 quantum number. Each orbital cannot hold maximum of 2 electrons. If there are 2 electrons in one orbital, they must spin opposite direction. Each subshell has fixed number of orbitals, that is S subshell having 1 electron, that is maximum accommodation of electron is 2. P subshell having 3 orbital, that is maximum accommodation electron in p orbital, that is 6. D subshell having a 5 orbital, maximum accommodation of electron is 10. F subshell having 7 orbital, maximum accommodation of electron, that is 14. Horn's rule of maximum multiplicity. The electron occupies degenerate orbitals singly before pairing the starts. That means orbital having same energy in a subshell like SPDF, it shows singly before the pairing. Each orbital of the same subshell get 1 electron first. All the single electron degenerate orbital have parallel spin of same direction. Pairing occurs only after the all orbital filled by a single electron. Half-filled orbital, that is P3, D5, F7. Fully filled orbitals are P6, D10, F14. Subshell are exact stable because symmetry is maximized, exchange energy, stabilize the system. For example, carbon Z equals 6, that is atomic number equals 6, electronic configuration 1s2, 2s2, 2p2. Written has 2p shows only 2 electron, not with the opposite direction in one orbital. Electronic configuration of atom, the shorthand representation. Example, hydrogen 1s1, helium 1s2. Here the number equals principal quantum number, that is n equals 1, 2, 3, etc. Letter type subshell SPDF. Subscript equals number of electrons in that subshell. Orbital diagram, box arrow representation. So each orbital is shown by one box, electron shown by the arrows with a spin plus half upper arrow and the minus half down arrow. Example, helium is having 1s2 electronic configuration represented like this. Electronic configuration of atoms. Example, hydrogen Z equals 1, 1s1 represented 1s1, helium 1s2, 1s2, lithium Z equals 3, 1s2, 2s1, 1s2, 2s1, beryllium Z equals 4, 1s2, 2s2, boron Z equals 5, 1s2, 2s2, 2p1, 2p1, up to neon Z equals 10, 1s2, 2s2, 2p6. Exception to the rule, some elements, particularly in the d orbital and f orbital in the periodic table, do not follow strictly the half-hour principle. This is because stability gained from the half-filled or completely filled subshell and can outweigh the energy difference between the orbital, that is chromium, the expected configuration argon 3d4, 4s2, but the observed configuration is argon 3d5, 4s1. This gives more stable for half-filled subshell. Expected configuration, this is the observed configuration. So the D5 configuration is said to be half-filled configuration. Why? Because the d orbital always contain maximum 10 electrons. So if the 10 having the 5 shows half-filled orbitals are extra stable in nature. Another exception for copper, the expected configuration argon 3d9, 4s2, but the observed configuration is argon 3d10, 4s1. This provide a more stable completely filled d subshell. Expected configuration 4s2, 3d9, observed configuration 4s1, 3d10. The 3d10 is said to be completely stable configuration of an electron in copper, shows extra stability. Reason for extra stability, symmetrical distribution of electron. The electron orbital try to stay as far apart as possible. Hounslow. A half-filled subshell like D5 or a completely filled subshell like D10 has highly symmetrical arrangement of electron. Symmetry reduces repulsion and increases the attraction from the nucleus, are more stable. Thank you.